Hello, I'm Lorenzo Seidenari and I'm an assistant professor at the University of Florence and co-founder of Small Pixels. Today I'm going to talk to you about preserving the quality of videos using deep learning. This is a joint work with my colleagues Leonardo Galteri, Professor Marco Bertini, Tiberio Uricchio and Professor Alberto del Bimbo. So let's take a look at this frame from the famous TV series Game of Thrones. All the audience asked Google why this frame was so bad, so terrible. So we all know why this happens. The thing is that when you want to stream some frames over the internet, you need to compress them, since bandwidth has a very high cost. Unfortunately, when you perform compression, the quality of frames can be degraded, in this case in a very dramatic manner. So it is very important when we digitize movies to take care about the quality, since we can then watch them and have a good experience, perceptually speaking. So every time we digitize videos, we can incur in this problem of compression artifacts. For example, we can think of the million of hours of digitized videos that we have, and this digitization process has been performed in the past, probably using a lower resolution than the one we are used today and using codecs which are not optimized as the one we use today. And of course, we enjoy videos in very high resolution screens like 4K screens. Another situation in which video is degraded is the one that we are well aware of. Since the recent pandemic, we spend a lot of time in front of our screens performing video conferencing. And of course, sometimes due to the lack of bandwidth, the perceptual quality of images is so bad that sometimes we really turn off the cameras. Okay, so how can we fix this problem? We propose to perform the following approach. We start from a very high resolution frame, high quality. We compress it as much as is needed. Then we transmit it, and at the receiver end, a deep convolutional neural network will restore the quality at its original version. Mathematically speaking, this is a process that we can see formalized this way. So we start from some XHQ, a high resolution sample, and this sample is compressed with some function C. This function, of course, is a codec. These obtain a low resolution frame XLQ. So our neural network will be trained to invert the compression function so that we can start from a low resolution frame and go back to the high resolution version of it. This has been performed by us, and we have presented this work in ICCV 17, and we did this for JPEG compression. So when we want to encode a video and we know that some of the parts are more relevant than others, we can do so-called semantic coding. In this case, we assume that some mask is provided. For example, in this case, we assume to have a mask of the pixels of the person. This way, the codec can allocate more bits for the foreground and less bits for the background, obtaining different qualities depending on the foreground and the background. The overall approach we are proposing here is to start from videos which are semantically encoded and restore them with a neural network to obtain an even higher quality. So our approach on the transmitter, we start from an original frame, without compression. We perform phase parsing with some convolutional neural network that is used to obtain a mask of the person, and then we perform semantic coding, obtaining an adaptive compressed frame. On the receiver end, we start from the semantic compressed frame and we apply a convolutional neural network to remove the artifacts, obtaining the final restored version of the frame. Our network is a generative adversarial network. In this approach, two neural networks are trained, a generator and a discriminator. The generator is trained to improve the low quality image and generate a high resolution version of it, high resolution or high quality. So the idea is that the generator learns to put back details into the frame that was degraded by the compression. On the other side, we see the discriminator, and the discriminator is trained to distinguish between actually high quality images and the ones that have been restored by the generator. During training, we are training the generator to fool the discriminator. So the generator will be optimized to generate images that are very high to distinguish from the actual high quality images, while the discriminator is trained to distinguish between real and fake high resolution images. The generator is trained using the following loss. The loss function for the generator will take into account the ability of the generator to fool the discriminator, and this is the adversarial loss, plus will incorporate two perceptual losses that are two functions that measure how good is the generator to keep the appearance of the foreground and the background. To do this, we will use two neural networks which are specialized for the face, VGG face, and the neural network which is general purpose since it's been trained to classify generic images, 1000 of categories. So let's take a look at the results. Here we measure the perceptual quality of the output frames of our process. The baseline that we see here in orange, it's the standard semantic encoding without the use of the artifact removal. We can see that here, since the metric we use measures the distance in some feature space of the restored frames from the original frames, we can obtain a 30% improvement. And here we use a different matrix that instead of computing the distance between the restored frame and the original frame, is actually measuring an overall quality or naturalness of the produced frames. Again, here the baseline in orange represent semantic coding without artifact removal, and the blue line is the result of the generative adversarial network applied to semantic encoded frames. And here we obtain an even higher improvement, 55%. Finally, a final remark on these results, we can see that when the encoding is not using masks, so here at the 0 mark in the graph, there's even a larger gain by applying our method. So I would like to show you some of these frames, and here we start from a compressed frame. As you can see, a lot of details from the face of the person are lost. There are a lot of quantization artifacts on the background, and the appliance on the right is very hard to distinguish. If we apply semantic coding, so using the saliency applied to the person, you see that the quality of the face is improved, but a lot of artifacts are kept in the background especially. Finally, if we apply our generative adversarial network, we can see that both the background and the foreground are restored. Interestingly, these frames that have a comparable perceptual quality with respect to the original one, they weight 1/3 of the original file size. So we can obtain the same experience on the user end with 1/3 of the bandwidth or the storage size of the file. Here I would like to show you a video in which we restore a highly compressed frame from a movie. So our approach is not only used on videos of video conferences, but can be applied to any footage. So finally, in this talk, we have shown a method to restore digitized video. So we know that when we digitize a video, we introduce a lot of compression artifacts. And this, unfortunately, will degrade the user experience. Here we have evaluated how we can improve the perceptual video quality using semantic coding on the transmitter end and generative adversarial network on the receiver end. We show that combining these two enhancements at the transmitter and the receiver end, we can improve two metrics that evaluate the perceptual quality of the image. And very interestingly, we can show that these frames, when have the same perceptual quality, they instead have 1/3 of the band used. So thank you for your attention. I hope you have liked our talk. If you are interested in this technology, please contact us either at our university emails or at our company email.